Okay, thank you. Can you hear me well? Yes? Okay, great. Thanks, Nicolau, for the introduction. So I prepared a few slides just to introduce the course. You know already that I will be instructing you about this course, and Pedro de la Torre will assist me in the exercise session. Uh, so as Nicola was saying, the morning will be lectures from my side between 9 to 10:55. Then we will have the coffee break, the other course, then lunch. This afternoon and Wednesday afternoon, there will be the exercise session for this course. And then there will be office hours between 4:30 and 5:30. The schedule of the course is the following. So each block is for a different day. So we will start with cosmic rays. In particular, some introduction about cosmic rays. Then we will go through gamma rays. These two first lectures are introductory to understand why we search for dark matter in cosmic rays and gamma rays. The third day, we will do an overview about dark matter on the point of view of evidence, gravitational evidences, general properties of dark matter density and velocity distribution. And then in the last 2 days, we will talk about indirect detection of cosmic rays with radiation. It will be mostly focused on gamma rays. And in the last day, we will talk about the indirect detection with cosmic rays, so in particular positrons, antiprotons, and anti-nuclei. If we have time in the last part of the 5th day, we will try to touch one specific case of a BSM model that is probably one of the easiest one, and we will see how we can combine indirect detection, collider, and indirect detection to study dark matter. So I prepared some notes that probably will be posted maybe today, later today. These are long notes that I have created using these references, so there is nothing really original. Maybe I will polish a bit the notes in the future. I put there basically all the calculations we're going to do. So one suggestion is don't be worried about writing everything I'm going to write in the blackboard. Just try to follow the procedure and the idea of what I'm going to teach. If you miss some calculation, don't worry, because you will see in the notes all the possible calculations. And I also prepared a few slides because it's easier just to show some plots and figures with respect to drawing in the blackboard. And the last point is, if you have any question, just raise your hand. And there will be also the office hour if you have any other question, okay? Okay, very good. So I think we can start. So we start with today with cosmic rays. So the study of cosmic ray basically starts actually in the end of 19th century with the discovery of natural radioactivity by Becquerel. And then, but the starting point of the history of cosmic ray is related to the end of 19th century and beginning of 20th century with the discovery of a constant and weak rate of ionization of ambient air that was detected using an electroscope. So the electroscope is this device, and basically you have a conducting material here. This is two leaf of gold foil, and if you have a charge here, basically the opposite charge is deposited in these leaves, and so for a Coulomb repulsive force, the leaves will be apart for some distance, and with a tool you can measure how distant these golden foils are. And basically the distance is then related to the charge that you have in the opposite part of the electroscope. And the origin of this sort of ionization of ambient air was a mystery for a lot of time, until several researchers brought discoveries that basically brought to the discovery of the origin of this ionization rate that was extraterrestrial. In particular, Theodor Wolff made one of the most precise electroscope, and then Victor Hess used this electroscope to do basically measurements of the ionization rate at different altitudes. In particular, using a balloon flight, he reached 5 kilometers of altitude, and he found that actually the ionization rate is not going down as expected if this radioactivity was coming from the ground, but actually was rising, was increasing, going higher in altitude. And the only possible interpretation is that this source of ionization comes from outside the Earth, so is extraterrestrial. Basically, this discovery, it's very, very important because this also brought physicists to make a lot of discoveries in particle physics. In fact, thanks to cosmic rays, Millikan and Anderson found the positron. Okay, so the first antiparticle detected at that time using cloud chambers and using cosmic rays interacting with the cloud chamber and measuring what's the trajectory of the positrons with respect to the electron. Okay, so the history of cosmic ray is not only important for astrophysics, but it's also very important for particle physics. Let me just close my audio here. Okay. Perfect. Okay, so after this very brief overview of the history of cosmic ray, we can start with some general properties about cosmic rays. So cosmic rays are relatively stable particles, or if you have a particle that, or an element that decays, the decay time of this cosmic ray should be at least larger than 1 mega year. And the reason is that in order to basically be detected on Earth, the decay time of the element or the particle should be at least larger than the typical propagation time in the galaxy. Because if you have a source of cosmic ray in one position of the galaxy, if this decays after even 10 years, basically this particle is not detected, okay? So cosmic particles are stable or long-lived, very, very long-lived, so decays after basically the propagation time scale. And they are divided into primaries and secondaries. So primary particles are the ones that are accelerated by galactic or extragalactic sources, so proton, helium, carbon, oxygen. Secondary particles are instead the ones that are generated after the collision of primary particles with the atoms of the interstellar medium. So positrons, antiprotons, possibly antinuclei, boron, lithium, beryllium, okay? And then how do we measure cosmic rays? So typically cosmic rays are measured in rigidity or in kinetic energy over number of nucleons. So rigidity, the reason why we use rigidity is that particles propagate in the galaxy where you have a magnetic field. And when particles move in a magnetic field, you know that you have the Lorentz force. The Lorentz force curves the trajectory of particles, so you can use that the Lorentz force is equal to the centripetal velocity. And so you can evaluate the radius that is called the Larmor radius, that is equal to gamma mv divided by qb. Okay, so there is a typical curvature of the particles when they move in a magnetic field. As we will see in the galaxy, you have a magnetic field, and so it's convenient this is actually, sorry, this is R and this is rigidity. So it's convenient to measure a quantity that is related to the Larmor radius, and in fact, the rigidity is calculated as momentum Ze, where Z is the charge of the element or the charge of the particle, and this is the Larmor radius multiplied for the magnetic field. Okay, so the fact that typically particles in the galaxy are affected by the presence of the magnetic field makes convenient to measure the cosmic ray energy actually in rigidity. Instead, the kinetic energy of the nucleon is convenient when you measure secondary particles. And the reason is that when you have cosmic rays, primary cosmic rays, interacting against the atom of the interstellar medium, this collision is basically proportional to the kinetic energy of a nucleon. So it depends on the number of nucleons that you have in the primary particle and in the interstellar medium atom. Okay? Perfect. The Larmor radius, actually, we can also write what's the typical scale of the Larmor radius. So it's typically around 1.1, 10 to the minus 6 parsec, for a momentum measured in gigavolt, and the magnetic field measured in microgauss. And then you have the charge. Okay, so just to give an example, for a 1 TeV particle in a magnetic field of 1 microgauss, the Larmor radius is basically 10 to the minus 3 parsec. This means that if you have inhomogeneity, so turbulence in the galactic magnetic field, the Larmor radius actually is very, very small compared to the size of the galaxy. And so the particle feels very efficiently this turbulence of the magnetic field. Okay? Okay, so okay, perfect. Okay, then some other quantities. So on the point of view, instead of the flux of cosmic rays is related to the density. So the density of cosmic rays is 4 over pi velocity, and then you have the intensity. The intensity has units of 1 over GeV centimeter square second steradiant. That is the same unit you see in these plots of the cosmic ray flux. So this is the quantity that is observed and measured by detectors. Instead, this density is the quantity that is typically found by solving the propagation equation. Okay, so we will solve the propagation equation to find the density of cosmic rays. We will evaluate the density at the position of the Earth, and we can find the flux with this relation. Okay. Now let's talk about the flux of cosmic rays. So as you can see, okay, this is the flux or intensity. So this I and the energy flux is basically the same thing. Energy flux here, it means that you have E squared multiplied for I. So in fact, E squared multiplied for this is exactly that units. And as you can see, the shape is more or less a straight line with some small differences, some changes. So here, for example, you go with a slope of e to the minus 2.7 up to the knee, that is around 3 PeV. Then there is a change of shape. This basically is related to the transition between galactic and extragalactic cosmic rays. Then the shape becomes softer, 3 to minus 3.1. Then you have the ankle, where it is back to minus 2.7. And then there is the GZK cutoff that is related to the interaction of cosmic rays with the CMB. Below GV, you have solar cosmic rays generated primarily from processes happening, basically the nuclear fusion in the sun. Then you have galactic cosmic rays from GV up to basically 10, 100 PV, so mostly given by acceleration of cosmic rays in supernova remnants in the galaxy. And then you have extragalactic cosmic rays that is not the main focus of these lectures. We will be focusing more into galactic cosmic ray. So if we focus on the galactic cosmic rays, AMS is measuring very precisely different species, and you can see that are basically all power laws, right? So it seems that there is a universality of the cosmic ray spectrum. And you don't see any change in the slope. But partially this reason is how you show the flux, because here you show the flux without any rescaling. And so the flux covers several orders of magnitude. So it's very, very important when you study the cosmic ray flux to study the flux rescaled by some power of energy, because this is the only way you can really see by eye the change of slope in the cosmic ray flux. Here, for example, you see that the rescaling by e to the cube, well, it's not that straight, the flux, right? So you have an increasing shape, flattening, softening, hardening, and cutoff, okay? So this is very important for, in this case, all the cosmic ray flux, but it's also very important for studying antiprotons or studying positrons. Okay. Okay, some other general properties about cosmic rays. The density of cosmic ray can be calculated with an integral in energy of the density. And this is roughly equal to 0.8 electron volt over centimeter cube. And this value is more or less the same of, for example, interstellar radiation fields. For example, starlight has more or less the same energy density, or the galactic magnetic field. So basically the three main components of the interstellar medium has more or less the same energy density, okay? Okay, then regarding the abundances of cosmic rays, the most abundant species is hydrogen. Basically 90% of cosmic rays is made of hydrogen nuclei, so basically protons. Then you have roughly 10%, 9% is given by helium nuclei, so alpha particles. And then all the other species are making basically a few percent of the remaining cosmic ray density. And when you study the origin of cosmic rays, you can be tempted to compare the cosmic ray flux with the elements present in the solar environment, in the solar system. So basically, you can compare the cosmic ray flux with the elements produced by the nuclear fusion happening in the sun. And if you do this, you see that there is a quite good match for proton, for hydrogen, actually for lithium, boron, beryllium, there is quite a large difference. For all the other elements, instead, the compatibility is quite good. So why there is this difference between, for example, boron, beryllium, and lithium, between cosmic ray and instead the solar system abundances? The reason is that you have not only primary cosmic rays, but you also have secondary cosmic rays. Okay, so in particular, you have for lithium, beryllium, and boron that are here. Also for nitrogen, there is quite a mismatch. So for secondary particles, you have a very important production that comes from, as I said, cosmic ray primaries, actually, colliding with interstellar medium, producing other cosmic rays that are lighter with respect to the initial one. This is basically nuclear nuclear interaction that destroy partially the initial cosmic ray. So interstellar medium is basically made as cosmic rays by 90% of hydrogen and 9% of helium. So basically most of these interactions are proton hydrogen, proton helium, but you also have, for example, oxygen or carbon colliding with hydrogen, and this produce lithium or beryllium or boron, okay? So this is the interaction that makes the red points in that figure much higher with respect to the density in the solar system made by star activity. Okay, so if this process is important, there should be a quantity that measures how much material a cosmic ray go through during the propagation. And this quantity is called the grammage. So the grammage is measured in units of gram over centimeter squared. Okay, so it's basically the amount of interstellar medium material that a particle goes through as a point of view of a surface during the propagation. And it can be evaluated as the integral of the density in the line of sight. Okay, so S is the line of sight that the particle is traveling. The rho is the density, electron volt over centimeter cube or gram over centimeter cube. You integrate this quantity and you can find the grammage. So now we can do a very simple exercise. So basically we take only one primary particle with a density Np and one secondary particle with a density Ns. So we imagine that in the galaxy we have only two species, one primary and one secondary. Primary particles and also secondary particles are affected by these nuclear interactions. The typical interaction length of this collision is called lambda. That is the mass of interstellar medium atoms divided by the cross-section for this interaction. And the average mass of interstellar medium atoms is roughly 1.3 the proton mass. And why it is 1.3? Because if you take 90% of hydrogen and 9% of helium, helium is 4 times the proton mass. So if you take a weighted average of these, you find 1.3 proton mass. And now we can write the differential equation for the propagation, basically for the propagation of the primary and secondary species with respect to the grammage. So this is the equation for the variation of the density with respect to the grammage for the primary component. So for the primary component, the only thing that can happen is that the primary collide with interstellar medium atoms, and so the number of primary particles is depleted by the presence of these interactions. If we instead take the secondary particle, you still have the depletion because also the secondary particle can collide with interstellar medium atoms. But also you have plus, so you have new particles that can be produced by the collision of the primary particle. And we parameterize this with the probability that the primary particle generates the secondary particle. And this probability should be proportional to the primary particle density. For the initial condition, we assume that in the galaxy we only have the primary particle, and the secondary one is created when primary particles start to collide with interstellar medium atoms. Now, if you solve this equation, and actually we are interested in the ratio between secondary and primary, you have this. Okay. And we can take values for the interaction length of the secondary and the primary, the ones, for example, for carbon, so lambda of carbon, that is roughly 9 gram over centimeter squared, and the one for the, for example, boron, that is a secondary species, is 10.4 gram over centimeter square. This comes from basically measurements of from scattering measurements. Instead, the probability that is, let's say, more uncertain, we can take the one that from a carbon you have a boron, exactly following those interactions. This is roughly 0.25. Okay, so solving this ratio with these numbers, actually no, I didn't put it here, you can find that then you can compare this ratio. Okay, this is the ratio secondary over primary. And you can compare this ratio as a function of the grammage with the measurement by AMS. For example, you can take the ratio of boron over carbon, that is roughly 0.3, and this is 0.3 and at 10 gigavolt. And as a function of grammage, you find that this matches the observations for a grammage that is roughly 10 gram over centimeter squared. So this is the typical grammage that primary particles can, the primary particles encounter during the propagation in the galaxy, okay? But now there is an issue, because we know that the galaxy is made by a very thin disk. So we can basically, let's say, make a simple picture of the galaxy as a cylinder with a very thin disk with half height of roughly h equal to 100 parsec. In this thin disk, you have gas, you have the interstellar medium, gas, you have the distribution of sources. And so particles are generated in the disk, and they travel across the disk. So you can be tempted to compare the density of the interstellar medium in the disk with the grammage that we just found. The problem is that this density in the disk is equal to 2.3 10 to the minus 3 gram over centimeter squared. And this number is much, much smaller with respect to the grammage. So this means that it's impossible that a particle generated from a source in the disk makes only one crossing of the disk. Okay? Because if this is the right interpretation, this number should be the same of the grammage. So this implies that actually particles should do multiple crossing in order to match that number. Basically multiply this factor by a very large number that represents the number of crossing done on the disk. And we can actually measure what's the typical time that particles should stay in the disk. And this is basically the grammage, 2 times the disk size, mu d, that is the density of the interstellar medium, and the velocity. And this gives a number that is basically 3 mega years. Okay, so the particles for 3 million of years do basically stay in the disk, should stay in the disk in order to match that number of the grammage. If this is compared, this is basically calculated in a length, in a typical propagation length for the particles in the disk, this is 1 megaparsec. Okay. But as I said, actually, the galaxy is not only made by a disk, but you also have a galactic halo where particles still propagate. We will see today that actually particles scatter against inhomogeneities of the magnetic field, and the size of this halo is still uncertain. It should be roughly between 2 and 10 kiloparsec. And so we can actually calculate what's the typical time that particles should stay inside this galactic halo. And this is roughly 6, 10 to 7 years. And we know this thanks to some radioactive nuclei. So in particular, the most important element in cosmic rays is the beryllium-10 that has a typical decay time 1.4 10 to 6 years. So by measuring the flux of beryllium-10, we can have an estimate of the typical time particles stay into the galactic halo. So particles stay for basically 3 million of years in the disk, but up to a factor of more than 10 in the halo. And when they exit from the halo, assuming that here you don't have magnetic field or turbulence, the cosmic ray escape for the halo and is lost. Okay. Perfect. Okay, perfect. Any questions so far? Okay. So what we learned is that the galaxy is made by a thin disk, a galactic halo that is much larger than the disk. You have primary particles accelerated by supernova remnants, probably mostly by supernova remnants. These particles travel in the disk for basically, let's say, a few million of years. But actually, they stay even more in the galaxy thanks to the presence of a galactic halo with a size of a few kiloparsec. And the particles stay in the galactic halo for basically the order of 60 million of years. And now we can try to understand how particles are accelerated by supernova remnants. And first of all, we can make an estimate if it is reasonable to think that supernova remnants are the most important accelerator of galactic cosmic rays. In order to do this, we can find basically first of all, we have to match the density of cosmic rays that, as I said, is roughly 1 electron volt over centimeter cube. And we saw that particles have to stay in the thin disk for 3, 10 to 6 years. Okay? Now we can evaluate the volume of the galaxy as the thin disk, actually 2 times the thin disk multiplied for the radius of the galaxy, that is roughly 20 kiloparsec. And we can evaluate, so the luminosity of cosmic rays that we have to match, that is the volume multiplied for the density and divided for tau. And this is roughly equal to 5 10 to 40 erg over second. So in order to match the observed density of cosmic rays, assuming that basically the cylindrical shape of the galaxy, we have to match this number. This should be the typical luminosity that a source should have in order to match the cosmic ray density. And if we take the supernova, a supernova when explodes, basically eject roughly 10 solar masses at a velocity of roughly a fraction of the velocity of light. So it's basically between 10 to 7, 10 to 8 centimeter over second. And this number gives basically supernova total energy that is roughly 3 × 10⁻42 erg per second. So just considering generally what is expected to match the density and what is expected by the dynamic of a supernova explosion, we see that these two numbers are different just by, let's say, 2 orders of magnitude. This means that an explosion of a supernova, and with an efficiency of the order of 1%, a few percent, of the order of percent, in the conversion of supernova energy into cosmic rays, you match the right bulk of dark matter, of cosmic ray density. There is another criterion that is called ILAS criterion that can be used to find if cosmic rays are good accelerator of particles, of supernova remnants are good accelerator of cosmic rays. And this relates the Larmor radius with the typical size of the accelerator. In particular, you have to satisfy this condition. So the Larmor radius should be smaller than the typical size of the accelerator. And this is easy to understand, because if you have a Larmor radius that is much larger than the size of the accelerator, the particle escape is not contained inside the accelerator, okay? The size of the accelerator can be found using the typical size of the accelerator, magnetic field, maximum energy, and using this number you can find that actually supernova remnants are indeed good candidates to accelerate particles. Okay, now we can go more into the detail of cosmic ray acceleration, and we can start with the second order Fermi mechanism. That is the mechanism theorized by Fermi in 1949. In particular, Fermi theorized that the galaxy is inhomogeneous, so the density is not homogeneous. You have clouds. These clouds are moving in random directions in the galaxy. And so cosmic rays, when they travel in the galaxy, they can encounter these clouds. And you have two types of, let's say, collision between the cosmic ray and the cloud. You have heads-on collisions, if they go one against the other in the opposite direction, or you have tail-on condition if instead the cloud is going in the same direction of the cosmic ray. And the idea of the second order Fermi mechanism is that it's more likely to have heads-on collision with respect to tail-on collision. In particular, the heads-on collision are increasing the energy of the particle. Instead, the tail-on is decreasing the energy. And so the fact that this one is more likely, is more frequent, this increases the energy of the particle. So in this image, I represent what could be basically the collision of a cosmic ray with a cloud. So this is a cloud moving with a velocity v in the direction from left to right. And you have a cosmic ray that in the reference frame of the galaxy has an energy E1 and the momentum P1. The particle enters inside the cloud with an angle θ1. And we can, first of all, make a Lorentz boost to find the energy E1 from the galactic frame to the frame of the cloud. And in order to do this, we simply take the gamma factor, basically the Lorentz factor, due to the velocity v of the cloud. And so E1 prime in the reference frame of the cloud is gamma times E1, that is the energy in the galactic frame, beta px. We are just interested in px because the velocity v of the cloud is in the x direction. Okay, so this horizontal axis that you don't see is actually the x direction. So we just consider the x direction here. And this is roughly equal to gamma E1 1 minus beta mu in, where mu is the cosine of the angle, and mu in is the cosine of theta 1. So mu in is the cosine of theta 1. This approximated symbol here is because we just assume that the particle is going basically at the speed of light, and so you can approximate the Lorentz boost using this equation. So now we have E1 prime, that is the energy when the particle entered in the cloud. In the cloud, you have an irregular magnetic field, you have turbulence. So the particles scatter against the inhomogeneities of the magnetic field. It goes into, let's say, a random walk. Let's say it's not exactly random walk, but basically it's that thing. Sorry. And then it exits from the cloud in this direction with an angle theta 2. In the cloud, the particle just feels the magnetic field. And you know that from the Lorentz force, there is no work done by the Lorentz force, because the Lorentz force is always perpendicular to the direction of the cosmic ray. So the Lorentz force is not making a work, so there is no change of kinetic energy, okay? This means that E2 prime, that is the energy just before the particle exit, must be equal to E1 prime. And then we can write E2 double prime, that is instead the change of reference frame for the reference frame of the cloud back to the reference frame of the galaxy. So this is gamma E2 prime 1 minus beta. Here I'm making explicit the signs just to be clear, where mu prime out is the cosine of theta 2 prime. So this minus is the minus of the Lorentz boost, and the minus beta, it is because it's the opposite velocity when you go back to the galactic frame with respect to the previous one, okay? Okay, now we can write the difference of energy, delta E divided by E, where delta E is E2 double prime minus E1 divided by E1. And this is equal to gamma squared 1 minus beta mu in plus beta mu out minus beta squared mu in mu prime out. Okay, this is just algebra, okay? There is nothing super clever in writing this. So the first thing to notice is that this delta E divided by E does not depend on the energy of the particle. It just depends on gamma, but gamma depends on the velocity of the cloud and the angles. Okay, there is no, basically no dependence with the energy of the initial particle. Now, the, the motion inside the cloud makes the trajectory of the particle isotropic. This means that if you do an average in the out angle, this average should be 0 in the cosine of the output angle. So we can make an average of delta E over E of mu prime, or the mu out. And this means that this must be equal to 0, and this must be equal to 0. okay? Because as I said, isotropized the motion inside the cloud. And so the output angle, if you take a lot of scattering inside the cloud, is basically isotropic. And so this equation, averaged over mu prime, becomes this. But now we have to also average over the initial angle, and the initial angle depends on the relative velocity between the particle and the cloud. Okay, so the distribution of basically the probability to get different angles should be proportional to the relative velocity, and if you write this with respect to mu, this is 1 over 2, 1 minus beta mu in. Okay, so cosine is mu in, then you put outside v, and so you have a v, the velocity of the cloud divided by v, but this is basically velocity of light, and so it becomes beta. And this 1 over 2 is just a normalization in such a way that the integral of the probability, the total integral, is equal to 1. And now, finally, we can do the average of delta E over E also with respect to the initial angle. And we can find that basically the relative increase of energy is 4 over 3 beta squared. Okay, do you think that this increase of energy is significant or not for typical velocity of clouds in the galaxy? What's the typical velocity of, let's say, what's the typical velocities that we have in galaxy? It's typically, let's say, 10 kilometers per second, okay? So if you take roughly 10 kilometers per second and you plug in this number here, this increase is roughly 10 to the minus 8. So it's a very, very tiny increase of energy. So if you have to basically compare this increase of energy with the kind of acceleration that we have to satisfy in the galaxy, and so you convert this energy with the typical time that the particles have to stay in clouds, this is giga-years. So you need a time scale of giga-years, so basically almost the age of the universe, to accelerate particles with the second order Fermi mechanism. So as you can imagine, this cannot work considering the dynamic and acceleration of cosmic rays in supernova remnants. But then there was a lot of work done by other scientists considering the idea of Fermi. And so physicists theorized the first order Fermi mechanism that is also called diffusive shock acceleration. In the diffusive shock acceleration, the idea is that you have a supernova explosion. The supernova explosion creates a lot of energy, and initially all the materia ejected by the supernova, it's moving at a fraction of the speed of light, so roughly between 10 to 3 and 10 to 4 kilometers per second. And when this material is moving, you have an upstream region and a downstream region. In the upstream, particles in the plasma are moving with a characteristic velocity u1. In the downstream, instead, you have u2. And u1 is larger than u2. And so the net velocity of the shock is u1 minus u2. So in particular, the upstream has faster plasma, but colder. Instead, the downstream has slower plasma but hotter. The first order diffuse shock acceleration works very well for accelerating particles, because when you have particles in this region, they are isotropized by the presence of turbulence in the magnetic field, and some of them basically goes into the downstream. And when they go in the downstream, they feel the plasma of the downstream as it goes towards them with a velocity that is roughly equal to us. So basically, this is like the cloud of the previous exercise as a head-on collision. So when particle goes into downstream, they feel a gain of energy. Then when they go isotropized again in the downstream, they happen to go again in the upstream. But also in this process, they feel the plasma of the upstream as it goes towards them. So again, you have a head-on collision as the cloud exercise. So also in this case, you have a gain of energy. So every time the particle goes through the shock discontinuity, you have a gain of energy. And if this happens a lot of times, you have a continuous gain of energy until the Larmor radius of the particle is too large with respect to the size of the supernova remnants. When this happens, the particle is not contained in the supernova shock and escapes into the interstellar medium. Okay? This is generally what happens. Then we can do the calculations. So as before, we take a particle that is in the upstream. It has an energy E and a momentum P. This is in the reference frame of the upstream. Then, during the motion in the upstream, there is a very large probability that this particle encounters the discontinuity and goes into the downstream. So the energy in the downstream reference frame is gamma E 1 minus beta mu, where gamma is related to us, that is the shock velocity. And here again, I made explicit the two sign. One is the Fourier-Lorentz boost, and the other one is because the basically the shock is going towards the particles. This angle mu is always positive. Okay, because if you take the x-axis, if you have to cross the downstream, the angle must be positive. Now we do again the same game, so we move again from the downstream to the upstream reference frame. So we do a boost of the downstream energy. This time mu prime must be negative. And it must be negative because going from the right to the left, if you take the x-axis from the left to the right, the cosine should be negative. Now we can evaluate the increase of energy. That is the difference between energy of the upstream minus energy, that is the initial one, divided by energy. Okay. And this time you can see that two factors are always positive. So this is positive because mu is positive, and this is also positive because mu prime is negative. So this time, the two terms always increase the energy of the particle. Instead, in the previous calculation, that one, the first, you could have a positive or negative difference of energy. And now, by doing the average of delta E over E into the two angles, mu and mu prime, you can find that the increase of energy is 4 over 3, this time beta. Okay, so this time the increase of energy has a power less with respect to beta, and this means that you have a much more efficient way for accelerating particles. Because basically this energy gain is of the order of 10 to the minus 3, 10 to the minus 2. That is exactly what you need as an efficient accelerator in cosmic rays. Thanks to the diffuse shock acceleration, you can also find a prediction for the slope of the spectrum of particles accelerated that is given by this relation between the downstream and the upstream velocities, and this is found to be roughly equal to 2. So this means that a typical spectrum of cosmic rays accelerated from the diffuse shock acceleration is proportional to e to the minus 2. Now, maybe you can wonder, but this number is quite different with respect to what we show in the flux of cosmic rays detected by AMS, because that slope was actually minus 2.7. So why these two numbers are different? We will see this later when we do the propagation. But basically, I can already tell you that during the propagation of particles in the galaxy, you have turbulence of the magnetic field, and this turbulence is parameterized with the diffusion, and the diffusion changes the slope of the flux by adding, or by, let's say, subtracting a factor delta, and this delta it's around 0.3, 0.6, okay? So thanks to diffusion, the detected flux of cosmic rays matches better the observed flux by AMS and other detectors. Okay, perfect. Any question? No? Yeah? I think so. You are asking what's the difference if you do first the average on the initial angle, and then for the final angle, that nothing changes. You should get exactly the same result. Other questions? Okay. So what we did is to study. So basically, what we are doing is actually a journey from the source, so the acceleration from the source. Now we have to do the propagation, so what happens to cosmic rays when they are injected into the interstellar medium and they encounter magnetic fields. And then the last step is the solar modulation, so basically cosmic ray enter inside the solar system. They feel the solar wind, and after the solar modulation, they are detected by our experiments. So as I said, in the galaxy, you have magnetic fields, and so we have to study what happens to a charged particle when it feels a magnetic field. Okay. Okay, so you know that when a charged particle encounters a magnetic field, you have the Lorentz force. In case you only have a magnetic field, the Lorentz force is written in this way. As I said, the Lorentz force is always perpendicular to the velocity, so the work done by the Lorentz force is equal to 0. This implies also the difference of kinetic energy of the particle is different from 0. So during the motion of the particle under a regular magnetic field, the velocity must be constant in amplitude, in magnitude. Then of course the vector changes, but let's say the speed remains the same. Then we can write the Lorentz force using the vector product, assuming that the magnetic field is only in the z direction, and it is regular, okay? So it's constant and homogeneous in the z direction. So writing the vector product, you have this. So we can take, in the z direction, you see that m gamma the vz divided by the t is equal to 0. What does it mean? It means that the vz over the t is equal to 0. And this is found as v multiplied for mu. Remember that mu is the cosine of the angle. And in particular, this mu is called, so the mu is the cosine of the angle. And this angle is the pitch angle. So it's the angle between the direction of the particle and the magnetic field. So in this case, you have x, y, z. The magnetic field is in this direction. You have an initial angle of the direction of the particle with the magnetic field. This is the pitch angle. The velocity must remain the same. This means that the mu over dt is equal to 0. So the pitch angle, in case of a regular magnetic field, must be the same. So the particle should make a trajectory like this around the z-axis, but keep always the same pitch angle. Okay, so this is what happens in the z direction, but what happens instead in the perpendicular direction, so in the x and the y? Well, you can write m gamma the v perpendicular over the t. The v perpendicular instead is the sine of the angle, and this can be written as the v perpendicular over the t is equal to q v perpendicular magnetic field over m gamma c. And this is v perpendicular divided by the Larmor radius. So in the perpendicular direction, the characteristic parameter is the Larmor radius. That is very well expected because, as we said, the Larmor radius is the typical radius of curvature of particles moving under a magnetic field. Okay. Then, in addition to the Larmor radius, that is another very important quantity, that is the Larmor angular frequency. So is the velocity divided by the Larmor radius. So QB divided by gamma MC. And this will be, basically this quantity is the quantity that typically you have in the cosine for the harmonic oscillator, okay, is that quantity. Okay, now we can write the three equations for the velocity. So you have m gamma dvx over t. Then you have m gamma dvy over t, that is set as a minus. And then you have the one on z, m gamma dvz over t, that is equal to 0. Okay, so these are the three equations of motions, the motion, okay? And now what we can do is that we can, for example, differentiate the first equation. So you have m gamma d2vx the t squared And we can take this and substitute it here. And if you do this, you can find a quite well-known equation, so the 2 v or x or y dt, that is equal to minus qb0 gamma mc vx or vy, or minus omega L squared Vx Vy. Okay, and this is the can be solved with a cosine or a sine, and so Vx is equal to V perpendicular cosine omega Lt, and instead Vy so what is this telling you? This is telling you that in the z direction the velocity is constant. Instead, in the x and y direction, basically the particle is moving a trajectory like this. So this is what happens for a particle moving in a regular magnetic field. The pitch angle does not change. The direction parallel to the magnetic field has no change of velocity. Instead, in the other two directions, you have basically an oscillation, and so you can find the equation with the cosine and then the sine. And the characteristic frequency is related to the Larmor radius. Okay. Then, unfortunately, the universe is not that simple. Actually, the galaxy is not that simple because you don't have a regular magnetic field. You have turbulence. You have a turbulence in the magnetic field. And so we have to study what happens to a plasma when it is affected by a regular and an irregular and a turbulent magnetic field. A plasma, first of all, is a gas that is heated in such a way that it loses the electrons. And so a plasma is a completely ionized medium with free moving ions and electrons. And this is exactly what you have in the galaxy. In the galaxy, except for the atoms of the interstellar medium, cosmic rays are free moving ions and electrons. And when you study a plasma under the presence of a magnetic field, you have to study the magneto-hydrodynamic waves and how they propagate into a plasma where you have a magnetic field. And when you study the dynamic of a plasma, you typically study these equations. So rho is the density, V is the velocity, P pressure, B magnetic field, and you have the continuity equation, that is basically what you have from fluid dynamic, momentum conservation, adiabaticity condition, induction equation, and the divergence of the magnetic field that is equal to 0. Okay, that is you should have it, of course. So in case you have no turbulence, basically you have a constant density, a constant magnetic field, a stationary plasma, V equal to 0, and a constant pressure. So this is what happens in the case of a stationary plasma without any turbulence. When you add some turbulence in the density, you are adding some delta rho, delta B0, delta V, and delta pressure. And typically what you do is that you develop your turbulence, you decompose basically the perturbation. So these are perturbations of the density, magnetic field, velocity, and pressure. And you can write your perturbation in Fourier modes. So for a generic perturbation delta F, that is a function of space and time, you can make Fourier modes as a function of the wave number. So this is the distribution of the Fourier modes in the wave number k and the frequency, angular frequency omega. And then you have a sum over basically cosine and sine. It depends on kx minus omega t. Okay? And then what you can do is that you can take the Fourier modes of the perturbation, you plug in these into your 5 equations, and you can find the solution for this distribution of Fourier modes, and you find the so-called dispersion relation. And the dispersion relation is a relation between omega and k. So, for example, in case of the sound waves, if you use the continuity and momentum equations, the perturbation of the density satisfies this condition, where Cs is the velocity of sound, and the dispersion relation is omega equal to Cs k. Okay, so this is just to give you an example of something that we know, that is sound. And it's very convenient to do the same also for the cosmic ray physics and what happens to the plasma under the galactic magnetic field. So we introduce a perturbation of the magnetic field, the B0. B0 is only, in this case, B0 we can make it still only in the z direction. We introduce a perturbation of the magnetic field, density, pressure, and velocity. And so you can develop your equations with the perturbation, and this is exactly what you have here. Okay, these are these equations, but where you develop the quantities around the perturbation, you take only the first order. And in particular, you can see why we get the simplest one. Okay, so you have the divergence of the magnetic field that is equal to 0. Assuming that the magnetic field is only in the z direction, we can take this. Then, as I said, you have a perturbation of the magnetic field, so you can develop the perturbation in Fourier modes. Sorry. And if you take the derivative of Bz in z equal to 0, you get that the B0 multiplied for kz is equal to 0. If you generalize this in all the 3 directions, so you make a magnetic field that is not only in the 3rd direction, you can find that there is a very general rule that the wave number, so the direction of motion of the wave, must be perpendicular to the perturbation of the magnetic field. Okay? And this is very important because when you have when you don't have any magnetic field, you have a wave propagating. This wave propagates isotropically, okay? Instead, when you have a wave or a perturbation with a magnetic field, the perturbation does not propagate isotropically, but it propagates anisotropically. So there are some preferred direction for the waves. Okay, this is something very important for cosmic rays. Cosmic rays moving in the galaxy, they feel the magnetic fields. This means that the propagation is anisotropic. So they follow some specific directions that depends on the direction of the magnetic field perturbations. Now we do 2 cases where you have the wave number parallel to B0. in this case, the solution to those equations gives that the perturbation of the velocity is equal to wave number Cs omega squared 0, 0, the Vz. Okay. And so you can see that you have that the perturbation in the velocity has two different directions. One that is parallel to B0, that is the Z component, for which the dispersion relation is basically the one of sound waves. But you have also one that is perpendicular, so the one in the X and Y direction, for which instead the dispersion relation follows this rule that can be written again with a very well-known v velocity k squared, where Va is the Alfvén velocity. That is very important for cosmic rays, where the velocity is equal to magnetic field square root of 4 pi and density, okay? And then you have instead the case where k is perpendicular to B0. In this case, instead, the motion is on the x direction with a velocity that is a composition of the sound velocity plus Alfvén velocity. So basically, you have this new velocity in case of cosmic rays, that is the Alfvén velocity, that as we will see later, is the characteristic velocity of the perturbations, and that this will give a process that is called reacceleration in momentum. And this comes from the effect of turbulence in the motion of the plasma. Okay. Okay, now I think I can remove this. Yes. Oops. Okay, now we will do a step forward to see how this turbulence, how this perturbation of the magnetic field can give you the diffusion coefficient. That is the parameter that is typically used in the propagation of cosmic ray to parameterize, as I said, basically the effect of the turbulence. So we take, again, a magnetic field that is only in the Z direction, and we take a wave number, so basically the propagation of waves is in the same direction of the magnetic field, and we take a pure Alfvénic wave propagating along the background magnetic field. Now we have to remember that the direction of the perturbation of the magnetic field should be perpendicular to the wave number, and this means that the perturbation must be present only in the X and Y direction. Okay, so there is no perturbation of the magnetic field in the Z direction. Now we can write again the Lorentz force equation, that in case of a perturbation of the magnetic field much smaller then the regular magnetic field is basically Q over C, Vy B0 minus Vx B0, and then Vx the By minus Vy the Bx. So assuming that you have that the wave is moving in the same direction of magnetic field, the perturbation is only in the xy direction. This means that this part of the velocity is unaffected by the perturbation, and so we can focus our study only in the z direction. So we can write m gamma dv z over dt okay? And we can substitute to Vx and Vy that equation over there on the top right. So Vx and Vy is going with the cosine and sine. And we can basically then you can it simplifies to m gamma v the mu over the t okay. And now we can also find that kz divided by omega t is roughly equal to the velocity of the particle, the Alphen velocity, and mu. But as I said, the Alphen velocity should be roughly of the order of 10 kilometers per second, while instead the velocity of the particle is close to the velocity of light. So this means that omega t can be neglected with respect to kz. Okay. And so we can find that the d mu over the t is roughly equal to omega L 1 minus omega squared 1 over 2 perturbation divided by regular magnetic field cosine of phi plus omega L plus minus k v omega t. Okay. This is the variation of the pitch angle with time in case you have a perturbation of the magnetic field. So it is not zero, as we have seen in case of a regular magnetic field. So the perturbation is changing the pitch angle of the particle. But if we take the variation of the magnetic field, the variation of the pitch angle for large enough times, since you have a cosine here, the variation of the cosine that is an oscillating function gives zero. Okay, so if you take very long times, the variation of the pitch angle in time is basically zero. Let me see. Okay. Now, in order to study the diffusion, typically we don't take the variation of, like the average of the variation of the pitch angle, but we take the average of the square of the pitch angle. So the variation of the difference of the pitch angle squared. And this is given by a complicated equation, but I will just to tell you what's the, after some approximation, you can find that this is equal to pi, the Larmor frequency squared, 1 minus omega squared, perturbation over magnetic field, delta t, and then you have a delta of kv mu minus plus omega. Okay, so the average of the square of the variation of the pitch angle is proportional to time. And this is exactly what you would expect for a diffusive process. Okay, so in a diffusive process, this should be exactly linearly proportional to the time, and is also proportional to the square of the perturbation. So the larger is the perturbation, and the larger is this quantity. Then typically the delta B over B is written with the spectral density, that is basically the distribution of the wave number of the waves. Okay, so basically this is equal to omega k dk. And this spectral density can be used to find the total energy simply by integrating omega k dk. So basically this omega k dk represents the energy contained in the range of wave numbers between k and k plus dk. When you study plasma physics, the fundamental quantity that is studied is exactly this one, is the spectral density. Then when you do cosmic ray physics, you try to find a relation between the perturbation of the magnetic field and the spectral density. Sorry, this I forgot a square here. Okay. So now by substituting delta B over B0 with the spectral density, we can find that d mu mu, that is basically a diffusion in the pitch angle, is given by omega L, 1 minus omega squared, okay, so this here you have a very important fact. You have the integration of the spectral density in wave number, and you have a delta. The delta implies that k must be equal to the k resonant, and k resonant is 1 over Larmor radius. So thanks to the delta, the integral goes away, and this means that the interaction of the plasma with the perturbation of the magnetic field happens only for a wave number, that is the resonant wave number, that is inverse proportional to the Larmor radius. And so the integral goes away, and we can finally write the diffusion in the z direction. Remember that we have a magnetic field, regular magnetic field, only in the z direction. And this is equal to v squared pi omega k resonant, and then the spectral density evaluated for k resonant. So the wave-particle interaction is only possible when the inverse of the Larmor radius is equal to the resonant wave number. Okay? Now, using basically studying plasma physics, so in order to understand what exactly is the dependence of the diffusion coefficient with the energy of the particle, we have to study plasma physics, and there are two different cases. There is the Kolmogorov case, where basically the spectral density is proportional to k to the 5 over 3. In this case, the diffusion coefficient is proportional to the rigidity over 1.2. Okay, so in case of the Kolmogorov plasma, the spectral density goes with the power of k to 5 over 3, and this gives a rigidity 1 over 2. Instead, in the case of the Kreiknam solution, you have that the spectral density goes with k to the 3 over 2, meaning that the diffusion coefficient should be proportional to the rigidity to 1 over, sorry, I wrote it wrongly. Sorry, this is 1 over 3. And this is 1 over 2. So from first principle, if you study plasma physics, you have a shape for the spectral density, and you can predict that the diffusion coefficient should stay somewhere between r to the 1 over 3 or r to the 1 over 2. And in fact, what we have from the study of cosmic ray is more or less in this bulk, okay? Exactly, the models give a rigidity with a slope between 0.3 and 0.6, okay? So the study of plasma physics seems to give roughly the right order of magnitude. Questions? Okay, so what we studied so far is that the galaxy can be assumed to be a cylinder with a very thin disk where sources are present. Sources generate, supernova remnants generates cosmic rays. Cosmic rays stay in the disk roughly a million of years, but in the halo of the galaxy, a factor of 10 more. Supernova remnants are the right astrophysical object to accelerate cosmic rays with the second order acceleration, also called the diffuse shock acceleration. The diffuse shock acceleration accelerates basically 10 to the minus 3 to the minus 2 for every crossing of the diffuse shock. When the particle escape and goes into the interstellar medium, they encounter turbulence due to the perturbation of the magnetic field. And studying the distribution of this perturbation with plasma physics, we find that the diffusion coefficient that you have to include in the propagation must be a power law of rigidity with a slope between 1.2 and 1.3. Okay? Okay. Okay, now, when you study the propagation equation, actually you don't have only diffusion. This is the propagation equation written with all the different ingredients. The propagation equation is an equation where you have to solve for n. N is the density of cosmic rays at a specific position in the galaxy with a specific momentum and as a function of time. The first term is a derivative in time, and this takes into account a fact where the density changes with time. For example, the pulsar injection of cosmic ray sometimes is parameterized by variation in time, but typically we take a stationary solution where you have reached an equilibrium in time, and so the n over dt is typically removed. Then you have the second object, this J, is the diffusion coefficient. So basically is the divergence of J is equal to the divergence of minus diffusion coefficient, the gradient of the density. This V instead is the reacceleration. The reacceleration is related to the explosion of supernova remnants. The supernova remnants are located basically in the thin disk, and when they explode, as I said, you have a lot of material that is ejected with a very high velocity, and this velocity propagates in the galaxy and creates these basically galactic winds. Typically, the velocity of the wind is taken to be a constant plus a gradient with respect to z. Okay, so it's a velocity that is basically constant on z, z equal to 0, but then increases with z. This gradient of the velocity generates an adiabatic losses, that is this term here. These are adiabatic losses related to the gradient of the convective velocity in z. Then you have reacceleration. Reacceleration basically follows from diffusion on the galactic magnetic field, but it is a diffusion in momentum. Okay, it's not a diffusion in space that we saw before, but it's a diffusion in momentum. It follows the same mechanism shown before, so we can relate actually the diffusion in momentum with basically the diffusion in space using assuming that the diffusion coefficient is proportional to the rigidity to the delta power. You have this delta factor. And the reacceleration is proportional to an Alfvén velocity, VA, that it is quite difficult to constrain because different papers typically finds values from 0 to even 40 kilometers per second. Then you have P dot that are energy losses. These energy losses are due to different processes. In the next lectures, we will see the inverse Compton scattering. This is related to the scattering of very energetic electrons against ambient photons of the interstellar radiation fields. And these upscatter these photons to X-ray up to gamma ray energy. And this collision is an energy loss for the electron because a part of the energy of the electron is basically go to the photon, to the low energy photon that is upscattered. Then you have the synchrotron energy loss. The synchrotron energy loss that is instead proportional to the magnetic field squared. So you have the Thomson cross-section, velocity of light, gamma factor, B factor, and UB that is basically proportional to the magnetic field squared, okay? So this means that in the center of the galaxy, where you have a factor of 10 larger magnetic field with respect to the average one in the galaxy, the synchrotron losses is a factor 100 larger. And then you have other processes that are important for low energy. So you have Bremsstrahlung, you have ionization, you have Coulomb scattering that we don't cover since we are interested instead in the more high energy part. For the interstellar radiation field that is important for inverse Compton, I just wanted to show you that the interstellar radiation field is typically modeled with the CMB, that is the lower energy part. Then you have the infrared. You have a part between infrared and starlight. So starlight is just the emission of light from stars. This light can be absorbed by dust and remitted at lower energy at infrared. And typically you can model the interstellar radiation field using black body distributions, where you have two parameters to calibrate. One is the normalization, and the other one is the temperature peak. And these are examples of the fit to the temperature and to the interstellar radiation field energy density. The black body approximation works, of course, perfectly well for the CMB. It works pretty well for the interstellar radiation field and for the peak of the starlight, and instead it fails to fit these lines emission. But typically, assuming 3 or 4 black body distributions is a good approximation and gives you the bulk of the interstellar radiation field. Now, talking about, okay, before going to this, I just wanted to finish the description of the different terms. You have the source term, for example, the source term for the production of a cosmic ray from supernova remnants or from pulsar wind nebulae or from dark matter. And then you have the scattering terms. So if you have the propagation for the species I, this takes into account the nuclear cross-section for a species J that is heavier, that collide against the gas and produce the species I. You have the decay of a J going into I, and this is proportional, of course, to the density of the J cosmic ray. But then, and this is plus because is an addition of number density, because the J goes into I. Instead, you can have the depletion of the density of the species I when the cosmic ray I interact with the gas and produces all the other cosmic rays. Or you can have the decay term if the I particle is unstable. In order to model this cross-section, you use scattering data that are quite uncertain, and there is a lot of effort at CERN to improve these measurements. If we talk about the typical decay, the typical time for the different processes, if you consider leptons, so electrons and positrons, this is the typical decay the typical time scale, so meaning that lower time scale means more efficient. And at low energy, you have diffusion, that is the most important one, but at high energy, you have the synchrotron, energy losses. For nucleons, instead, diffusion is the most important one. Okay, by far, if you just want to approximate your propagation equation and you just take diffusion, you basically make the bulk of the propagation. And the last thing that I wanted to say today is an overview of the results that we get with these models. Different papers find a good match between our models and the data. The data are very diverse because you have species, primary species with a lot of elements, and also for secondaries we have a lot of data that covers actually 3-4 orders of magnitude, and our model can fit pretty well the data, but there are still some open problems that we will see in the next lectures. And finally, I just wanted to tell you that, as I said, the diffusion halo, the size of the diffusive halo, is not very well known. The main reason is that there is a very well-known degeneracy between the diffusion coefficient and the size of the diffusive halo. So typically you can fit your model with different D0 and L. So typically with an increasing D0, you can fit the data increasing L. So with the D0, so the diffusion coefficient at 1 GeV, just below 10 to 28, you can fit well with the size of roughly 1 kiloparsec. If you increase the diffusion coefficient up to 4, 5, 10 to 28, you can still fit well the data, increasing the size of the diffusive halo to 8 kiloparsec. The shape, instead of the diffusion coefficient, does not change dramatically if you change the size of the diffusive halo. So you can always find a pretty good fit to the data with different L, and the shape is actually more complicated with respect to the simple power law we have written for the diffusion coefficient. So we probably have two breaks, one at roughly 5 gigavolt, and the other one at a few hundreds of gigavolt. That are probably due to transitions of the turbulence in the magnetic field for different energies of the cosmic rays. Okay, questions? Okay, if not, we are ready for the coffee break. Okay. non so come fare. Vai.
No, non toccare niente.
Perché ce l'avevo da vabbè, spengo da qua il microfono.